Okay, I paused the recording, so let me start again because that part has not got recorded. So today we are going to discuss the contents of this note, which talks about FP representations of the absolute Galva group of a P field. So recall that a P field is either a finite extension of QP or of the Laurent series field FP par series T. So that's what a P field is. What is the absolute Galva group of a P field? You take this P field K, choose some algebraic closure, or rather separable algebraic closure of your P field, and the group of all automorphisms, all K automorphisms of K tilde. K tilde is this chosen separable algebraic closure. The group of all K automorphisms of K tilde is the absolute Galva group of K. And so what is the representation? Now that's a very basic question. It doesn't have anything to do with P fields. It has nothing to do with this particular kind of Galva groups. It is just a question. It has something to do with groups, abstract groups, and a field. So you can talk about the representation of a group over some field. So what is that? Now, let us suppose that G is a group and F is a field, right? So if a representation of G, or an F representation of G more precisely, is just a homomorphism from G to the group of all linear automorphisms of some vector space over F. So F is a field. You can talk about vector spaces over this field. Let's restrict ourselves to finite dimensional vector spaces. So these vector spaces have linear maps between them, and of course you can talk about linear maps from the vector space to itself, and those which are bijective are automorphisms of that vector space. They form a group which is sometimes called GL of V if the vector space is called V. So a representation of a group G over a field F is just a homomorphism from G to GL of V for some finite dimensional vector space V over the field F. So these are what representations are. Now, so I was just talking about abstract groups, but these Galva groups are sort of not quite abstract groups. They are profinite groups. And when you have a group with a topology, a topological group, you talk about representations which are continuous. So that homomorphism is required to be continuous. So when you talk about continuity, you have to have topologies on the source and the target. On the source is a topological group, so there's a topology. The target is GL of V, where V is a finite dimensional vector space over your field F. What is the topology on GL of V? Now, we are going to look at cases where this GL of V carries the discrete topology. So sometimes, of course, this V is going to be a vector space over some topological field, and then it inherits, or it has some topology compatible with the topology on the field. This V itself has some topology, so it's a topological vector space. And this GL of V might have a topology. We are not looking at that case at all. In our case, GL of V is just a discrete group, but the group of which we are taking representations. The Galva group, that is a profinite group. But actually today, we are not even going to look at a Galva group. That's going to be day after tomorrow. So today, I'm probably just going to confine myself to this situation. So let's look at this section 2. And so the situation is the following. I have, is this going to work? Oh, this is not going to work. So I'll use my finger to, okay. So here's the notation, right? Let me use this then. The notation is that we have yeah. Okay, so I have a prime number P, and I have a finite extension K of the field Fp. Q is going to be the number of elements in this field, and I also have a finite extension L of this field K. Right? Or till now, everything is very simple. I have a prime number P, a finite extension K of the finite field Fp. Q is the number of elements in the finite field K, and L is a finite extension of K, and F is the degree of L over K. So if I have a finite extension of a finite field, it's always Galva. Sigma is the Galva group, and not only is it Galva, this group is cyclic. Not only is it cyclic, it has a natural generator. It comes with a generator, and that is this sigma. What does sigma do to an element X of L? Sigma, of course, has to be an automorphism of L because it's an element of the Galva group. Capital sigma. And this little sigma, what it does to an element X of L is to raise it to the power Q. Q, remember, is the number of elements in the base field little k. So that is the setup. Now, in addition to this, in addition to this little k and little l, I have a subgroup T of L star. Of course, L star is also a finite field. So, L is a finite field, excuse me, not L star, which is not a field. It's just a group. So, but because the L is a finite field, L star is a cyclic group. It is a cyclic group. It doesn't have a canonical generator, but it is a cyclic group, and I'm taking T to be a subgroup of this cyclic group, right? And if E is the order of this group, or order of this group T, then I will have Q to the F is going to be congruent to 1 modulo E. Now, you see, this is something which is completely, it's very, this highlighted congruence should be clear to you. So why should it be clear? Now, so it says that E divides Q to the F minus 1, right? That's what this congruence means. And why does E divide Q to the F minus 1? Because E is the order of this group T, and Q to the F minus 1 is the order of this group L star. What happened to this now? The order of the group L star is Q to the F minus 1, because the number of elements in the field L is q to the f, because q is the number of elements in the field k and f is the degree of L over k, right? So I'm going to have this q to the f congruent to 1 modulo E. Right. This inclusion of T in L star, I'm actually sometimes going to call it theta. Because I'm going to consider maybe other characters of T with values in L star. So a character of a group is a homomorphism from that group into the multiplicative group of some field, right? And in this case, the field is L and the group is T. So this inclusion, of course, is this inclusion, which I'm calling theta, is of course a homomorphism, and it can be viewed as a character of T. Fine.
Sir?
Yes.
Sir, character is not always a homomorphism, I think, because I have studied in representation theory that
Right.
character is not always a homomorphism.
Right.
Yes, sir.
So there are two meanings of the word character. You should not confuse them. So the one,
Yes, sir.
yeah, the first meaning that the meaning that I'm using is that it's a homomorphism from your group to the multiplicative group of some field. So it's a homomorphism by definition.
Okay, sir.
There is another
Okay,
meaning.
sir. Okay.
No, wait. There's no hurry. There is another meaning of the word character, and which is also very current in representation. What is the noise? Which is also very current in representation theory, and that is, sorry, there's some explanation. Yeah. So when you have a representation of a group, you can follow it up by taking the trace. So a representation is a homomorphism. Then you take the trace of those elements, and that thing is called the character of this representation. That character need not be a homomorphism. So that's a different kind of character. Okay. Right. Good. Good. So yeah. So this character theta, of course, is a homomorphism. And now let's look at this. Let us, what is this G equal to T times sub Q sigma? Now, let me explain what this is. So for that, you have to know what the semi-direct product is. So let me explain what the semi-direct product is. So for making a semi-direct product, you need a group, let's call it G, and you need another group, let's call it A, and you need an action of G on A. So G and A are groups, and G is acting on A, which is to say that you are given a homomorphism from G to the group of automorphisms of A, right? In this case, you can form you can take the ordinary product of the sets A and G, A cross G, but you can make it into a group in a new way. It's not, you can of course make it into a group by defining multiplication component wise. That's the ordinary product. But there's another kind of product called the semi-direct product, for which an action of G on A is required. And that's why I said you need, in order to define this semi-direct product, you need a group, you need two groups, and one of them acting on the other. So you need G, A, and an action of G on A. Now, so how do you define the product of two elements? A1, G1 times A2 G2. How do you define this product? Not component wise, but when an action is given, the first component is not going to be A1 A2, it's going to be A1 times G1 acting on A2. G1 is an element of the group G, A2 is an element of the group A acts on G, no, it's the other way around, G acts on A, so G1, so what is it? Yeah, G1 acting on A2 makes sense. So A1 comma G1 times A2 comma G2 is A1 times G1 acting on A2, comma G1 G2. So the second component is just the product of G1 and G2. The first component is not the product of A1 and A2, it is the product of A1 and the action of G1 on A2. So that is what the semi-direct product is. So now I have written here G as a semi-direct product of T and sigma. So I have to first say, what is the action of sigma on T? Of course, there's an action of T. Sigma is a Galva group, right? Here it is. It's the Galva group of G L over K. So there's an action of sigma on L. There's also an action on L star. But is there an action on T? And the answer is yes, there is an action of sigma on T. Because the action of sigma on L star takes T to itself. L star is a cyclic group. T is and a cyclic group has a unique subgroup of a given order. Of course, the order has to divide the order of the cyclic group in question. But once you have specified the divisor of the order of the cyclic group, there's a unique subgroup of that order, right? So every sigma in capital sigma stabilizes capital T, and therefore you get an action of T or of sigma on T. Okay, and that is why you can take this semi-direct product. I'm writing a little Q because what this action is, it raises everything in here it's written. It takes x to x to the power q. Here x was in L, but it could be in L star. It will be the same formula, of course, or it could be in T. So the point is that if x is in T, then x to the power q is also in T. And anyway, so that gives an action of sigma on T. And therefore you get this semi-direct product. So for this action, okay? Now, so our sigma is of course commutative. Not only is it commutative, it's actually cyclic with a canonical generator. And T is also commutative because it's a subgroup of L star. But this G need not be commutative, right? So it's a semi-direct product. For example, let's look at the first example of a semi-direct product would be you take a group of order 2, you make it act on a group of order 3. A group of order 3 consists of 3 elements, right? 1 tau squared. And a group of order 2 will consist of just 2 elements, 1 and sigma. How do you define? There's a unique non-trivial action of this group of order 2 on the group of order 3. If you think in terms of homomorphisms, then this group of order 3, the group of automorphisms of this group of order 3 consists of just 2 elements. There's the identity automorphism and the automorphism which takes tau to tau squared. Tau squared is also equal to tau inverse. Because tau times tau squared is tau cubed, which is equal to 1, because the group is of order 3. So from a group of order 2, namely 1 sigma, to a group of order 2, namely the group of automorphisms of this group of order 3, there can be only 2 homomorphisms. There's a trivial homomorphism, and there's the other homomorphism, which takes 1 to 1, of course, but sigma to the non-trivial automorphism of this group of order 3, the one which takes sigma tau to tau squared or tau inverse, which is the same thing. So that is the first example of a group of order, of a semi-direct product, because when you take the semi-direct product for this action, what you get is S3. The symmetric group on 3 letters can be viewed as a semi-direct product of a group of order 2 acting on a group of order 3. Okay. So now all this was to tell you, so I want to finish this. This G, which has been defined like this, it's, although T and sigma are commutative, this G need not be commutative. And you'll see that it's commutative if and only if this Q is congruent to 1 modulo E. Okay, so that's how you look at the definition. This Q, so it's commutative if and only if this action is trivial, and the action is trivial if and only if Q is congruent to 1 modulo E, right? Here's this Q. If this Q is congruent to 1 modulo E, then the action is trivial because E is the order of the group, and right. So that's the only case where you get this G is going to be a commutative group. Now the problem we have is to classify all FP representations of this group G. Now, why are we interested in this group? So those of you who remember this theory of tamely ramified Galva extensions of local fields will remember that the Galva group of such local fields, such tame extensions, has exactly this kind of shape. It's this kind of a semi-direct product. Okay, so that is what is behind this. That's the reason why we are considering this case. Okay, so that's the problem, and there's some further notation which is required. So what I'll do is, I think there's no point in, I'll try to give an overview of what is happening. Okay?
Yes, sir.
Right. So now if I have a character chi from T to L star, then you have the order of this chi, right? What is the order of chi? What does it mean? It means, this, you can think of it as the order of the image of chi. The image of chi is a finite subgroup of L star, and that has some order, and that is called the order of chi. So a quadratic character is one for which the order is 2. A cubic character is one for which the order is 3, and so on. So d chi is the order of chi. Then you have R chi and S chi. What are these numbers? These are numbers. So once you have d chi, this number, you can form the group Z mod d chi Z. star. Z mod d chi. Z is a ring, and this star says that you look at the multiplicative group of that ring. Of course, the prime number p and also this prime power q, which is p to the f, right? They're integers and they have images in this group. And as such, their images will have some order. And that order, those orders are being called R chi and S chi. So P and Q are sort of fixed for the discussion. It's chi which is sort of varying, and for varying chi, I get D chi, and I get R chi, S chi, and so on. Then I have T chi, which is T modulo the kernel of chi. Now, the kernel of chi is, of course, a subgroup of T. It's a normal subgroup because T is actually a commutative group, and I can I can go modulo this kernel of chi to get this quotient T chi. And what is sigma chi? Sigma chi is the action of sigma, is the kernel of the action of sigma on T chi. So the sigma acts on T. It also acts on the kernel of chi, because that's the sigma actually, capital sigma, this Galva group, acts on every subgroup of L star. Like T is a subgroup of L star. This kernel of chi is a subgroup of T, so it's a subgroup of L star. And therefore, this capital sigma acts on the kernel of chi as well. So it acts on the quotient T modulo the kernel of chi. Right? Now, when a group acts on some other group, there is always a kernel of the action. After all, an action is just a homomorphism, and a homomorphism has a kernel. So this sigma chi is the kernel of the action of sigma on T chi. Now, this sigma chi is what? It's a subgroup of sigma, right? And sigma is a cyclic group. It's generated by this little sigma. And therefore, this, what you can check now with all our definition of S chi, R chi, etc., is that this sigma chi, namely the kernel of the action of sigma on T chi, is generated by sigma to the power S chi. It's clearly generated by some power of little sigma, right? Because every element of capital sigma is some power of little sigma. But a little checking is required to see that this is exact. It's that part that it's generated by sigma to the power S chi. Okay.
Yes, sir.
Yeah. So S chi is also the size of the sigma orbit chi bar of chi. What is the sigma orbit chi bar of chi? Now, you see, first of all, so this sigma acts on L star. So it acts on the set of all characters of T. T is fixed. Chi is varying, even L star is fixed, right? And you look at all characters chi of T with values in L star. Then I can think of it as a module over sigma. Sigma, given a character, I can apply little sigma or any element of capital sigma to L star, and I get a new character. Because these elements of capital sigma are automorphisms of L star, right? So, so S chi is also the size of the chi orbit, of the sigma orbit, excuse me, of chi. Then you have this group G chi. This semi-direct product can be viewed as a subgroup of G. G was this semi-direct product, and you can view of this as a subgroup of G. And this quotient, where the action is actually trivial, this is a quotient of G sigma, and it's commutative. So you just go through what the definitions of these numbers D chi, R chi, S chi is. These are the orders. And these groups, so they depend actually only on the sigma orbit chi bar of chi, not on the character chi itself. So normally maybe we just should say chi bar in the notation, but let's keep it light and let's just use chi, where what you actually mean is chi bar. Okay, so let chi also stand for the faithful character coming from chi. Remember, what is this T chi? T chi is this quotient. And chi is a character of T. Why should I get a character of T chi of this quotient? Because the quotient is exactly by the kernel of chi. So when you go modulo the kernel of a homomorphism, you have an induced map on the quotient, right? And I'm saying that that induced character is still going to be called chi. So that's this section. Let's look at the next one. Remember, our problem is to classify all FP representations of G. So before doing that, we will classify, first of all FP bar representations of G. Now, here is something that happens quite often. You want to do something over some field. So instead of doing it directly over that field, you do the corresponding thing over an algebraic closure or a separable algebraic closure. And then there is some Galva action there, and you sort of understand that Galva action to conclude whatever you wanted to do initially. So concretely, in our situation, we are interested in FP representations of this group G. Instead of FP representations, we are looking at FP bar representations first. So I've called them L tilde representations because they are defined over a smaller field L tilde, where L tilde is to L, you adjoin an F prime root of unity of order, a primitive root of unity of order F prime, where F is what? F, when you write, no, F prime, excuse me, what is F prime? F, you already know what it is. F is the degree of the field extension L over K. But what is F prime? F prime is the part of F in which is prime to P, so to speak. You write F as a product of prime powers, you erase the power of P which occurs there because you also got a fixed prime number P, right? You suppress that power, and whatever remains, that product, the product of all prime powers dividing F except the power of P, so that product is called F prime. So one needs a root of unity of that order, and so VPF, you already know what it is the power of P, the exponent of P in F, in the prime decomposition of F. So, as I said, first we are going to, so L tilde is of course, a finite extension of L, right? Obtained by adjoining a primitive F prime's root of unity. And so first, and L itself is a finite extension of little k, which itself is a finite extension of fp. So ultimately, I'm going to go down from L tilde to fp. I'm interested in fp representations. First, I'm looking at L tilde representations because that's more convenient. And they're easier to write down because I have this root of unity in that field. And once I've done it, we'll come down to the level of fp. What happened?
Sir, your screen is not visible now.
Right, so let me do it again. Sorry, just a moment.
Okay, sir.
Yeah. Just a moment. Oh, I've been logged out. This is not good. Just wait. Yeah, maybe our Wi-Fi is not working properly. Can you see it now?
No, sir.
That's not good. Just a moment, huh?
Okay, sir.
Yeah. Share content screen. Start broadcast. It's working now, right?
Yes, sir. Now it is. Yes, sir. Yes.
Okay, good. So somehow we are managing with this kind of internet. So let me make some remarks. The group G that I have just defined, what kind of a group is it? It's a group, let me just go back, because I want to say that we are looking at not the simplest possible case of a group. The simplest kind of group is a cyclic group. But we are looking at the next simple case. Namely, our group G has this group subgroup T, which is cyclic, and the quotient is sigma, which is also cyclic. So it's an extension of a cyclic group by a cyclic group. So that's a very simple kind of group. And we are going to determine FP representations of this group. And this is how we proceed. So, so as I said, first we are going to determine L tilde representations of this. L tilde is L to which I will join a primitive f primeth root of unity. And these representations, L tilde representations of G, they are going to be parameterized, meaning we are going to give a bijection of these representations with the set of pairs chi bar lambda, where chi bar is going to be a subset, not an element, but a subset. So it's a of this group Hom T L star. That's a group of all characters of T, right, with values in L star. And chi bar is going to be a subset of this group of characters. It's actually going to be the sigma orbit of a character chi. So how do you get a chi bar? You take any character chi from T to L star. In fact, we already have a distinguished character, which is the inclusion of T in L star, right? T is, after all, a subgroup of L star. But even though it's a subgroup, we are looking at all possible characters of T with values in L star. And then these characters, on the set of these characters, this is the set. There's an action of sigma. because there's an action of sigma on this L star. So there's an action of sigma on the group of all characters with values in L star. And if I'm an element sigma of chi, then I have its orbit under sigma, which is chi bar. Okay, so that's going to be the first component of my pair, chi bar lambda. What is the second component? Lambda. Lambda is an element of L tilde star. Now, L tilde star is a group, and this element will actually be an element of order dividing F S chi inverse. F, as you know, is the degree of L over K, and S chi, if you recall, is the order of Q as an element of the group Z mod D chi Z star. So this is how things turn out to be, you know. Okay, so now I said they're going to be parameterized by these pairs. So to every such pair, I have to attach a representation like this, an irreducible representation, excuse me, not just an irreducible representation. And to every irreducible representation, I have to attach some pair like this. So let's start. So let's start with a pair chi bar lambda, where chi bar is like this, lambda is like this. Okay. So choose some chi in chi bar. After all, chi bar is the orbit of some character, so choose a character. And then you get this psi, you get this homomorphism, or this character of sigma chi. Sigma chi was what? It was the kernel, no, not the kernel, it was, let me just go back and see what it was. I think it was, yes, the kernel of the action. So, sigma chi, g chi. Sigma is the kernel of the action of sigma on t chi, right? So, from a character chi of t with values in L star, I get a character psi of sigma chi with values in L star, L tilde star, which takes, in order to define a character of a cyclic group, what do I have to do? In fact, of a cyclic group which happens to have a specific generator, I just need to tell you where that generator goes. And it's allowed to go to any element whose order divides the order of my generator. My generator here is sigma to the power s chi, right? That's what I had said. That's what this group s chi is generated by. And that's why I had chosen lambda to be an element whose order divides not so what is it? Yes. So the order of sigma to the power s chi, what is it? This order is, of course, the order of sigma divided by s chi inverse. And that's exactly the order of lambda. That's why I have chosen an element lambda of order whose order divides the order of sigma to the power s chi. Okay. Right? So now I've got a character of S, a sigma chi. I've got a character chi of T actually, but I can think of it as a character of T chi. So if I got a character of sigma chi, which is this, and a character of t chi, which is this chi, then I get a character of the product. I get a character of the product, right? So I get a character. And because this product is actually a quotient of g chi, I get a character of g chi, which is this twisted product. It's not a direct product, it's a semi-direct product. And if I get, so this semi-direct product, of course, is a subgroup of what? It's a subgroup of G. Now, this G chi was a subgroup of G. So if I have a character of this subgroup, I can induce it to a representation of the whole group. Right? So now I'm assuming that you know what an induced representation is. But if you don't, it's explained here in quite a bit of detail. So you just need to look at it. So here in number 10, it's described perhaps what it means to what this rho chi bar lambda is. So this is the rho chi bar lambda. So it's defined here in this number 10. So the brief description is this, that it's the induced representation from this character of g chi. What is the character of g chi? It comes from a character of g chi bar. Where does the character of g chi bar come from? It comes from the characters chi and psi. Chi is given to me because I'm looking at a pair in which the first component is the orbit chi bar of some chi. So I choose any chi in that orbit chi bar. And where does this psi come from? It comes from chi as well as this lambda which was chosen. Okay, chi gives me this s chi, which gives me sigma to the power s chi, and so on. This is what the pair chi bar comma lambda.
Sir,
Yes.
Sir, I have one doubt here. That you have taken that this is the chi tensor psi chi lambda is a character of g tilde chi. This is character.
G chi bar. Yes.
Now, sir, this is rho x lambda is a induced character or induced representation. According to me, it should be the induced character rho chi bar lambda. It should be character of this g chi bar.
Yeah. So you see, you have been you are more used to the language of characters, and
yes, sir.
That is the same as the language of representations. So maybe you induce a character to get a character of the group to get a character of the big group. But you can also induce representations of a subgroup to get representations of the big group.
Okay, sir.
So it's you can think of it either way, but here in this subgroup, for this tensor product is a character in the sense in which it's a homomorphism. And it can be therefore viewed as a representation as well, a one-dimensional representation. And then you induce it, so you'll get a representation of some higher dimension, and that dimension can also be computed from whatever.
Okay, sir. Now I understood that you are using this character as a representation from
right.
Okay, because this is a homomorphism. Yes, sir. Okay.
Yeah, it's a one-dimensional representation, or
okay, sir.
What is it? Rank 1, degree 1 representation.
Degree one.
Yeah.
GL1C L star.
That's right. But it's GL1 L tilde here. It's not C.
Yes, sir.
We are not looking at representations over the complex numbers. Yes. We are looking at representations over this field L tilde, which itself is a finite extension of L, which is a finite extension of K, which is a finite extension of FP.
Okay, sir.
Because
Okay, sir.
ultimately we are interested in representations over FP. So we are starting with the representations over L tilde, and then from those we are going to get representations over FP. Now we have cooked up one way of getting representations over L tilde, which is to say that if I start with a pair like this, chi bar comma lambda, then I get a representation rho chi bar lambda, this induced representation, right? So that's what we have done till now. So there's a small checking to be done, which is that this rho as defined seems to depend on various things. What we need to check is that it depends only on this pair chi bar comma lambda that we started with. And here is a small checking. It's also something which tells you what this induced representation is. If you're not already familiar with it, here is an explicit description of the induced representation. Okay. Now, so that's number 10. And you just need to read it. So what is it doing? It's saying that this rho chi bar lambda depends only on chi bar lambda and not on any choices that we might have made while defining it. Well, I don't quite know what choices we have made. We haven't made any choices. So we're just making it explicit actually. Okay. The next observation is that this representation that we have got now this rho chi bar lambda is an L tilde representation of G, of course. It's absolutely irreducible. So what does absolutely irreducible mean? It means that this L tilde, let's think of it as a subfield. L tilde is a subfield of FP bar. FP bar is an algebraic closure of FP. So you have FP, which is contained in K, which is contained in L, which is contained in L tilde, which is contained in FP bar. So if I have representation over L tilde, of course I can tensor it with any extension of L tilde to get a representation over that extension. So from a representation over L tilde, I get a representation over FP bar. Now it may happen that some representation over L tilde is irreducible. And maybe it has been checked in number 10 here that this representation that we are looking at is actually irreducible. So you might have a representation over L tilde, which is irreducible, but when you tensor it with FP bar, it might no longer be irreducible. So if it is still irreducible over FP bar, you say that your representation is absolutely irreducible. Okay. So that is what is being checked here for this rho chi bar lambda. Let me stop for a few minutes and you can just see if you have any questions. Okay, so let me continue. So the first part of this assertion in 11 is that this rho chi bar lambda is not only irreducible, it's absolutely irreducible. And it determines this pair chi bar lambda. Meaning, if you have two distinct pairs, they'll give rise to distinct representations, rho. So in some sense, the mapping from the set of these pairs to the set of absolutely irreducible representations over L theta, this mapping is injective. So that's a checking which is being done here. Okay. Fine. So I've got the set of pairs, I get the set of representations, I've got an injective map from the set of pairs to the set of representations. In order to say that it's bijective, I need to show that it is surjective, which is to say that every FP bar representation, every irreducible FP bar representation comes from such a pair. So we have, let me just summarize it once again. What is being done? In this number 9, we are attaching a representation rho chi bar lambda of the group G. It's an FP bar representation. Let's just think of it as an FP bar representation. Forget about L tilde for some time. It's an irreducible FP bar representation of the group G attached to the pair chi bar lambda. That's what we did. So we give a mapping from the set of pairs to the set of representations. And then we check that this mapping is sort of injective because it determines the pair. Meaning we recovered the pair chi bar lambda from the representation rho chi bar lambda, right? So that's what it means for it to be injective. We recovered this from this. Next, we are saying that every representation, absolutely, irreducible FP bar representation of G comes from such a pair, which is to say that the mapping from the set of pairs to the set of representations is surjective. So if it's injective and surjective, then it's bijective, and that's what we wanted to prove. We wanted to parameterize all representations of the group G over FP bar, and that's what we have achieved. Now, how is that an improvement? In what sense can we say that we have solved the problem of classifying all FP bar representations of this group G? We have done it because, after all, these pairs, chi bar lambda, these pairs are easy to determine. After all, what is chi? Chi is just take any homomorphism from T to L star. That's T. We know the group T. It's a cyclic of some order, order E actually, but and we know the right. So chi is just some homomorphism, and this lambda. Where is lambda here? Lambda is some element of order dividing F as chi inverse. So that's also something which you can easily write down. Okay, so these are the these two ingredients. The first, chi bar and lambda, or chi and lambda, they are easy to enumerate. So you can look at chi bar, the orbit, and you can look at the representation of G attached to the pair chi bar, comma, lambda. And these are all. So we have determined all the representations of G. That's the whole idea. And that is what this, this thing here is saying. This number 15 is a summary of what has been done. So it says that the set of irreducible L tilde representations of G. G is this group, the semi-direct product of T and sigma. Sigma acts on T by raising everything to the power Q, and then therefore you can take the semi-direct product. So this set of irreducible representations is a natural bijection with a set of pairs chi bar lambda consisting of the sigma orbit chi bar of a character chi. So first you just look at all characters chi, and once you have chosen a character chi, then you get various quantities attached to it. You get the order of this character, which is called D chi. You get R chi, you get S chi. What are these numbers? R chi was the order of P, the prime number P, in the group Z mod B chi Z star. What was S chi? Is the order of the element Q in the same group. It's Z mod D chi Z star. So once you have chosen chi, you get this S chi, and lambda is an element of L tilde star of order dividing F over S chi, F divided by S chi. S chi is also, it also happens to be the order of the orbit of chi. Okay. So this is the main proposition. The set of irreducible L tilde representations of this group is in natural bijection with this set of pairs. Actually, such a statement is not very informative. You have to say what the bijection is in order to make it useful. So here is the part which tells you what that bijection is. So to the pair chi bar comma lambda corresponds this representation rho chi bar lambda, where which is an induced representation from G chi to G, where G chi is this group, is the semi-direct product of T and sigma chi, not sigma, but the subgroup sigma chi. Sigma chi is what? Is the subgroup generated by sigma to the power S chi. S chi, remember, I've already defined it. I mean, one way of seeing what S chi is the orbit of, is the number of elements in the orbit of. Yes?
Yes, sir, you're right.
Okay. So
I'm saying that the S chi is order of the orbit of chi. That's you're saying.
no, S chi is not order of chi. That is D chi. S chi is the order of Q,
orbit of
Q in Z mod D chi Z star. Or it's also the order, meaning cardinality of the orbit of chi. Chi bar is the orbit of chi.
Yes.
Right? So
yes, sir.
This is G chi, is this semi-direct product, T semi-direct product with sigma chi, not sigma, that would be G, right? G is the semi-direct product of T and sigma. Where G chi is a subgroup, it's the semi-direct product of G and the subgroup sigma chi. Sigma chi is generated by sigma to the power S chi. And so it's an induced representation. For induced, it's induced representation from this character. And what is this character? Chi, we already know what it is, but this Psi, what is that? That is the character of this sigma chi, which takes sigma to the power s chi to lambda. Lambda is the second component of the pair, right? So that is what, that's a summary of what we have just done. It gives a bijection. It determines all FP bar, irreducible FP bar representations of this group G. All FP bar representations of this group G. Right? G, remember, it has a subgroup T, which is a normal subgroup, and this quotient modulo this normal subgroup is this group sigma. And this is exactly what the Galva group of a tamely ramified extension of P fields looks like. Right? But for all this analysis, I mean, all this algebra, I should say, that connection with P fields is irrelevant. We are doing pure group theory here or representation theory. We are determining all representations of this G over FP bar. Okay, so that is this here. That's the summary. Now, you might say, okay, I mean, these pairs consist of the character, and it so happens that this group G comes with some natural characters chi. You have to choose a character chi in order to make such pairs and then write down these representations corresponding to the pairs, right? So the group T actually comes with some natural characters. For example, it comes with the representation with the character theta, which is just the inclusion of T in L star. So, and this lambda, I mean, in order to define a representation of G, I need not just a character of T, but I also need this second component, lambda, right? I need not just chi, but also a lambda. But this lambda is an element of order dividing something, something. I can always take lambda to be trivial. Trivial meaning I can take it to be 1. So I can take the representation chi to be this theta, which comes with T, so to speak. And I can take lambda to be 1. Then I get a representation rho theta bar comma 1. It's an absolutely irreducible L tilde representation. And you can compute its degree. Its degree is equal to the order of Q bar in this Z mod E, Ez star. So so this group G, as we have defined it, actually comes with a very natural representation, which is this this rho theta bar comma 1. And the degree of that representation is equal to the order of Q in this group Z mod Ez star. E, of course, is the order of T, and Q is the order, Q is the number of elements in the field K. So the order of this L star is Q to the F minus 1. Okay. Fine. But we were interested in not in L tilde representations or F bar representations, but FP representations. Why are we interested in these FP representations of this group G? So for that, you have to go back to some of our previous lectures. In fact, just the last week, we are interested in classifying primitive solvable extensions of our P fields. And we had seen that they correspond to pairs consisting of irreducible FP representations of of the absolute Galva group of your P field. That's the first. That was the first component, and there was a second component of that pair. Let me. I don't need to recall today what the second component was, but the first component was an FP representation of the absolute Galva group. Now, so in order to study these FP representations of the absolute Galva group of a P field, I'm looking at FP representations of groups like G. That's the reason. That's the motivation. Okay. So now I want FP representations pi of this group G. Okay. And so let's look at phi, capital Phi, which is the Galva group of L tilde over FP. L tilde is a finite extension of L, which is a finite extension of K, which is a finite extension of FP. In any case, it's a finite extension. Being a finite extension of FP, it is Galva over FP, and I'm calling phi the Galva group. But this Galva group acts on the set of irreducible L tilde representations of G by conjugation. What does that mean? So these irreducible L tilde representations of G, I have parameterized them by the set of pairs, right? Pairs like chi bar lambda. So if I have a pair chi bar lambda, then actually I get another pair, which is chi p bar, comma, lambda p. Chi is a character of the group T. Chi to the power p is also going to be a character of the group T. And chi bar is the orbit. I can take the orbit of chi p bar as well. Similarly, lambda is an element of some L tilde star of order dividing something. But lambda to the power p is also going to be an element of the same group of order dividing the same thing. So from a pair chi bar lambda, I can always construct a pair chi p bar lambda p. Okay, so in some sense, my Galva group phi, this phi, to give an action of phi on some set, I just need to tell you what the action of the generator of this phi is. Of course, let's call it little phi, this generator. And that little phi takes x to the power p for every x in L tilde. So in order to give you an action of the group phi, I just need to tell you what little phi does to this row. So if I have a so if rho corresponds to the pair chi bar lambda, then rho after its action by little phi corresponds to this pair chi p bar lambda p. So that's the action of phi on the set of representations. And what is the set of FP bar? Not FP bar. FP representations, irreducible FP representations of G. They are in bijection with the set of phi orbits for the action of phi on the set of L tilde representations of G. So that is what I meant when I said that if you want to do something over FP, you first do it over some Galva extension and make the Galva group act on the whole situation and look at the orbits. So this is an example of what is called Galva Descent. So let me explain once again what is going on. So I have this field FP, and I have this Galva extension L tilde, finite Galva extension. And I have the set of all L tilde representations of the group G. What I'm interested in are the FP representations of the same group. So what I do is I make the Galva group of FP of L tilde over FP. That's phi. I make it act on the set of L tilde representations of G. So the set of L tilde representations of G, we have parameterized it by the set of pairs chi bar comma lambda, right? So in terms of these pairs, this action of phi on the set of L tilde representations is given by sending the pair under this generator little phi of capital phi. This generator little phi sends the pair chi bar comma lambda to the pair chi to the p bar lambda to the power p. Okay, so now I've got not only the set of all irreducible L tilde representations of G, but I've got an action of the Galva group phi of L tilde over Fp on this set. So whenever I have an action of a group on a set, I have the set of orbits. And it's the set of these orbits which is in natural bijection with the Fp representations of G. These are the representations which I wanted to parameterize right at the beginning. And now I've found a solution to this parameterization, namely it's the set of all phi orbits for this action. So if it's a parameterization, I should be able to say what is the degree of the representation in terms of the degree of the orbit, in terms of the orbit. So the orbit will have some number of elements, and each of those Hello, can you hear me?
Yes, sir. Yes, sir. Now I can hear you.
Yeah, okay. Right. So, so these orbits for the action of phi on the set of pairs is what parameterizes Fp representations of G, irreducible Fp representations of G. Okay, so maybe I'll just see what, if the next thing is a different topic, then we'll take it up the day after tomorrow. Yeah, no, it's not, it's the same thing. Yeah. So the next thing is, how do we compute the number of elements in the orbit? So this is what explains how you compute this number of elements. And here's the summary of what we do, what we have done. So the set of irreducible Fp representations pi of this group G, which is the semi-direct product of T and sigma, under the action of sigma on T, consisting of raising every element to the power Q, right? I mean, the generator's little sigma of capital sigma acts on T by raising an element x to the power Q, x to the power Q, sending x to the power Q. So the set of irreducible Fp representations of this group G is what we are interested in. We are saying that this is a natural bijection with a set of phi orbits R. R is a phi orbit. So there's a bar. This bar on the whole thing means that it's some orbit or equivalence class or something, right? But the orbit itself is of a pair, of the first component of which chi bar is itself an orbit. It's a sigma orbit. Chi bar is a sigma orbit of some character chi. So these orbits are such an R is an orbit of a pair chi bar lambda, where this chi bar is itself a sigma orbit of some character chi, and this lambda is an element of order dividing this, where S chi is this. S chi is the order of Q bar in Z mod D chi Z star. And D chi, of course, as I said earlier, is the order of chi. And I'm saying that they're in natural bijection. What is the bijection? So pi corresponds to this R if and only if when I go to L tilde, I get the I get this direct sum. It's the sum of all representations in that orbit. The representations in that orbit, right? So each of them is absolutely irreducible, as we have seen earlier. And when I take the direct sum, I'll get a representation which is not irreducible over L tilde, obviously. I mean, if the number of elements in the orbit R is more than one, then this representation is not going to be, because it's the direct sum of a certain more than two representations over L tilde, it's certainly not irreducible, right? But when viewed as a representation over Fp, it is irreducible, right? Okay. So if R chi denotes the order of this, and W lambda is this degree, then the degree of this pi is LCM of this. So that's also some computation which has been done here. And that's about all that I wanted to say today, except that maybe one should have looked at some examples. And these examples are treated here. So for example, yeah, where is it? Yeah, so here are some examples. It's take P equal to 2, F equal to 3, E equal to 1. Look at some simple cases like this. And this T is actually the trivial group. So what is the group G going to be like? If T is trivial and G is the semi-direct product of T and sigma, then of course G is going to be equal to sigma. And sigma is Z mod 3Z. Why? F is equal to 3. And sigma is always a Z mod Fz, right? So what is L tilde? L tilde was defined in terms of L by adjoining a certain primitive F primeth root of unity. Here F prime turns out to be 3, because F prime was, you take F and you knock off, you remove the powers of P from F. But there are no powers of P in F. So F prime is equal to F, and L tilde is just obtained from L by obtaining a primitive cube root of unity. And what are the possible characters of T? Of course, there's just the trivial character, because T itself is just the trivial group. So it's the trivial character. Let's just denote it by 1 instead of calling it chi. And so once the character chi is chosen, you have to look for a lambda. Lambda has to be an element of L tilde star of order dividing something of order dividing, what is it? F S chi inverse, whatever. So it turns out to be an element of order dividing 3, maybe in this case. So the only things which are possible are 1 is cube root of 1 and its square. So we get 3 L tilde characters. I mean, they're going to be, they should be normally representations, but we know how to compute the degrees of these representations, and the degrees turn out to be 1. So they are being called characters. And so they are, I mean, because there are 3 possible pairs, right? There's only 1 chi, but 3 possible lambdas. So there are 3 possible pairs, chi bar, lambda. So we get 3 representations, row, this row, this row, the third. So that these the 3 representations. Okay. And now there is this phi, which is acting on the set of these 3 representations. It so happens that these 2 are in the same orbit, because as you can see, this lambda raised to the power 2, p is 2 here, right? So the second one is,
Sir,
yes.
here L tilde is cube root of unity. L tilde is. Sir, what cube root of unity we will take? I mean, we will take 1 omega squared. Which one will we will choose for L tilde?
So it's a primitive cube root of 1. So
okay, sir.
One of them, you are calling them omega and omega squared. I'm just calling it this. What you are calling omega, I'm calling it this cube root of 1. So I could have written omega if you want, right? It's
okay.
And it doesn't make any sense to ask which one I take, because they are all sort of conjugate under the Galva group. So you take any in some. So the correct answer is you take any, and provided, well, I mean, you're not allowed to take 1, because that's not primitive. But take any,
yes, sir,
cube root of 1 other than 1.
I can take omega or omega squared. I can choose any.
Yeah, but this omega and omega squared, etc., you are thinking of them as complex numbers, perhaps. These are not complex numbers here. You see, you are working over this field. L is a finite extension of F2. L is a finite extension of F2. So these are not, you should not think of, I mean, it's certainly not, they're not complex numbers. They are the analogs of these things over finite fields, right?
Okay, sir.
Okay, so we get these 3 characters, and these 2 are in the same orbit, and this is in an orbit by itself. So you get 2 orbits, and these are the only irreducible L tilde representation. So we get 2 FP representations, namely the trivial representation corresponding to this. This is the trivial representation, I mean, of degree 1, and the action is trivial, and the irreducible representation. This is of degree 2, because it's a sum of these 2 things here. It's the sum of these 2 things. Over L tilde is the sum of these 2 degree 1 representations. Okay, and because this one is not absolutely irreducible. Anyway, so when you take this representation pi, which is not absolutely irreducible, as I said, it's acting on this. Of course, it's a representation on of what's it? Why is it acting on? Yeah, because we're looking at F2 representations, and it happens to have degree 2, so it's acting on F2 squared, right? And so you can take this semi-direct product, and you can check that this semi-direct product is actually isomorphic to the alternating group on 4 letters. So you see, this is what I call an Z mod 3Z example, because here the group G is Z mod 3Z. But because I had taken E to be 1 and F to be 3. But I can do something else. I can take Q to be, I can take F to be 1 and E to be 3. I can take, just as an example, we are looking at small examples. So I can take F to be 1 and E to be 3. And then you'll see that L tilde is just your L. You don't need to adjoin any primitive, whatever root of unity. And you get G is still a cyclic group of order 3, but it doesn't have a canonical generator as here. So I'm calling it A3 instead of Z mod 3Z. And so I'll get I'll still get 3 irreducible representations, these ones. So here, theta is what? Theta is the given character. I mean, this T by definition was a subgroup of L star, and theta is the inclusion. So now I'll get these 3 representations. All of them happen to be of degree 1. And as before, these 2 happen, the last 2 happen to be the same orbit. So I get the trivial representation and this degree 2 representation, and the group is still isomorphic to A4. So I would advise you to just before the next lecture, day after tomorrow, you look at the next example, which is in number 24 here, right? That's a slightly more complicated example because we are looking at S3 instead of A3. This S3 example, we just look at this and then we will meet on Wednesday, right?
Yes, sir.
Are there any questions?
Yes, sir.
Okay, right. See you then.
Okay, sir.
I'm ending the meeting.
Okay, sir.